Welcome to the Tantray physics classes. Today we are discussing one more challenging problem. The problem is like that. Is a current carrying conductor infinitely long, and the current follows this path, and finally it goes to this straight wire and then goes back to infinity in this fashion. The current carrying conductor is infinitely long and current flows like this and follows this path and finally goes back to infinity. What we have to do, we have to find the magnetic field at this point, because of this frame, current frame. That's our question. Magnetic field at O. The distance of O from this straight conductor is d, and from the edge of this conductor it is on this side minus a, on this side plus a. I mean, this distance is a and this distance also a. If we take this point to be origin, right side distance are positive and left side distance are negative. That's our question. A current frame like this, and we have to find magnetic field here at this point. So what we have to do, we have to find the magnetic field due to this straight conductor, also due to this straight infinitely long conductor, and due to this short finite conductor whose length is a plus a to a. That's our question. So basically this question can be split into parts. Why not find magnetic field due to this long conductor first, and then due to this part? So point number one, let us understand what's the magnetic field due to this conductor. This is the finite conductor. Let me find the magnetic field of this conductor. Current carries current I, and I have to find magnetic field here at this point P. Let me do this first, then I will do a few more steps, and then finally I will come to this problem so that it can be understood very easily, right? So what is magnetic field here? Derivation, leaving aside the derivation, I want to write down the magnetic field due to this finite current carrying conductor here at this point. What we do, it is a point lying outside the domain of this conductor. It's quite outside. If the point would have been here, it would have been within the domain. If it would have been here, it will be on the boundary. Here on this side, it will be within the domain of the conductor. On this side, it is out of the domain of the conductor. What we do is that we just extend it like this and draw a perpendicular from here. Suppose this perpendicular distance, shortest distance of the conductor with the point P, let me suppose it is A, okay? It is A. First of all, let me find the direction of the magnetic field here. The direction of the magnetic field is if the current is extended in the forward direction, hypothetically, current in the forward direction, and from conductor to the point P, A's direction is taken downwards from conductor to the point. This is the direction of A. I cross A inwards is the magnetic field. I cross A, you cross I into A, cross product, the magnetic field will be inwards. So here magnetic field will be quite inwards. So that's the direction part. So how to find the direction of the magnetic field at a point? You have to wind I into this distance, I into A, and watch where the thumb goes. It is I cross A is inwards. Magnetic field is inwards. But the point is, how much is that magnetic field? So what we do is, this end of the conductor is connected like this, and this end is also connected like this by the dotted lines. This is angle theta 1, and this is angle theta 2. What is the magnetic field here? B equal to, which is obviously inwards, that is mu 0 I, this one, divided by 4 pi, this A distance, shortest distance, sine theta 2, this whole sine of this whole angle, minus sine theta 1. This is the formula. This is the formula. That's all. We have found the magnetic field due to a short conductor in the outside domain. Draw a perpendicular, extend the line, draw a perpendicular. This is theta 1 with one edge line, theta 2 with another edge line. So, you know, mu 0, you know, it's a constant, magnetic constant. permeability of a free space, I is the current flowing, and 4 pi A is the shortest distance between the conductor direction and the point. That is all. So second point. Okay, if this, I will extend this only to the second point so that it becomes quite easy to do. Second point, if it is a conductor like this, current carrying conductor, and the point is not outside the domain, it is within this domain, inside, anywhere, here, anywhere, point O. What we do in that case, draw a perpendicular here on the conductor as we have drawn there, but there we had to extend the conductor. Here we just draw the line onto the conductor. So let us say it is A. Connect this point with this edge line, connect this point with that edge line. Suppose this is theta 1 and this is theta 2. Now what is the magnetic field here? First off, direction, it is I direction. It is from here to here downwards, it is A. I cross A, again inwards. You have to wind I into A by the cross product. You can, if you have a cross product of I and this shortest distance, but this shortest distance has to be taken downward direction. I cross R inwards. This is I, this is R inwards. Okay. Now what is B? Same formula. Mu 0 I by 4 pi A sine theta 1 plus sine theta 2. You have to remember this. When the point is inside the domain, you sine theta 1 plus sine theta 2. This we have to remember. Okay. Third one. These two things have to remember so that we can attack that problem in a very efficient way. Okay, third point is something like this. Have a look. If you have a conductor quite long in one direction, and you have a point here, point P, I want to find magnetic field here. Suppose current is this, and first of all, this end is defined, but the other end is not defined. It goes to infinity. What we do is that again we have to draw the line dotted so that we can draw a perpendicular. Suppose this is okay, A, again A. Connect this edge line. This is theta 1. Connect that edge line, but that edge line is far off. That edge line is far off. So if that edge line is quite far off, this angle becomes 90 with that edge line because that's quite far off. So what is the formula now? The formula is B equal to, of course, the direction, I cross R. Always I show inwards. I cross R is also inwards. So it is mu 0 I by, again 4 pi A sine theta. No. First of all, sine 90. What it makes with that extended edge line. But that is sine 90. Because that edge line goes far off and line goes down and down and down and down and finally it becomes 90. It is sine 90 minus sine theta. This angle minus this angle. Sine of this angle. Sine of 90 minus sine of this angle. So that the integration of the actual question is within this angle. Conductor is within this angle. So this whole angle minus this angle. Sine of this whole angle minus sine of this angle. So that actual integration that we do for this or actual magnetic field that we have to find is within this angle, because within this angle there is a conductor. Something like this, the conductor. Here's a point. Draw a perpendicular. This angle and this angle. When you say sine of this angle minus sine of this angle, that means you are integrating over this domain. There, in that domain, there is the inductor. There is the conductor, sorry. This is second point. That's all. This is third point, and all these concepts we will use here to find the magnetic field due to this current carrying conductor. Okay. Now let us write part wise. What is magnetic field? Okay, first of all, I want to find magnetic field due to this conductor at this point. It's a conductor and it is extended, already extended. You draw a perpendicular, and perpendicular distance, it is A. A is here, and it is a long conductor. It is the edge line. One edge line makes angle alpha, and other edge line, if I see, that is up infinity, that is 90. So what is the magnetic field due to this conductor? And what is the direction of that magnetic field? Current is downwards. It is I, and it is A is here from conductor up to the point O. It is A, I cross A outwards. So it's an outward magnetic field. So B equal to mu 0 I by 4 pi A, this one, distance, sine of that angle in which the edge line makes with the longer one in the infinity, that is 90, minus sine alpha. That is all. We have already talked about a conductor. One end extends to infinity, other end is defined, and so we can write it mu 0 I by 4 pi A sine of 90 minus sine of this alpha. But there's one more conductor, so it will be 2 times the same magnetic field will be here. This magnetic field and this magnetic field get added up here, right? Okay, but the magnetic field is outwards, I cross R. Now what is the magnetic field to this short conductor? It is theta here, so the point lies within the domain of this short conductor here. It is theta, it is also theta. And here, this distance from here to here is D. It is D, this distance is D. Right? Okay. Now, that is, and the magnetic field is out, that is it is I cross, this is D, I cross D inwards, sorry, that is inwards. So it was out, and the magnetic field to this is in, I cross this distance in. So that is minus mu 0 I by 4 pi D. That is this distance, D, shortest distance point in the conductor, sine theta plus sine theta. Because this point lies within the domain of this conductor, so you have to add to sine theta plus sine theta. Now, let me simplify this. This is 2, it is B is equal to mu 0 I by 2 pi A sine 91 minus sine alpha. Alpha is 90 minus theta. Alpha is total angle minus this theta, that is cos theta. Sine alpha is cos theta, because alpha is 90 minus theta, so it is minus mu 0 I by 4 pi D twice sine theta. 2 to the 4. Okay, now what should I do? What to do here now? Okay, B equal to, okay, it is mu 0 I by 2 pi A. It is 1 minus, what is cos theta? Cos theta is theta, this base by this hypotenuse of this triangle, base by hypotenuse, that is D divided by root of A square plus D square. Here, this hypotenuse, that is D, this is A, or this is A, this is A square plus D square root. Okay. Minus mu 0 I by 2 pi D into sine theta, perpendicular by hypotenuse, that is A by root of A square plus D square. Something like this. Okay. Now, answer is very compacted, simplified form, so I have to get this to the answer expression. So what should I do? That's B equal to, what should I write here? So I will do something. So mu 0 I 2 pi A, this one, but is not, A is not here, but I will take it common factor. Also D I will take common factor. So I will see what I'm going to write here. there is what should I write here? So it is 2 pi a is here, here d is missing, so I should write d here. Two pi a d, 2 pi a is common, so it's a, d is missing here, so I will write d here. Here there's no d, so I will write d here, d square by root of a square plus d square. Here d is there, but a is missing, so I will write minus a square by root of a square plus d square. Here d was missing, so I had to write d. Here d was missing, there I should write d square. Here a was missing, d is here, a was missing, so I had to write a square here. You can check it out, it's no problem, and you can do it in 2 steps. So what is b equal to? That is mu 0 I by 2 pi a d, d minus common, a square plus d square, denominator a square plus d square root, so it will become root of a square plus d square in the numerator. It is minus common, say a square plus d square, in the denominator there is a root of a square plus d square, but finally it will become in the numerator a square plus d square. This is the answer to that question. I got the answer, otherwise this would also have been a good answer. Anything earlier than this equation, final equation, could be the answer, but I try to get the final answer given in the book. Thank you for watching the lectures, and you can watch this lecture on my YouTube channel or on my app, and there are many questions on my application, Tantray Sir Physics classes, and also I am continuously doing this series of what you call is challenging questions, challenging physics problems continuously. You can watch the lectures on YouTube or on my app. Thank you.